Sick. Thank you. Yeah, the trial quiz, Emily, will open up. I can't remember exactly how it lines up, but something like 11:05 or 11:10 or something. It will open up in here if you want to take it. But I'm going to go over the homework. I think that most people are probably ready to go to do the homework. So let's go ahead and take a look at it. Last week we did the first 3 questions, which is chapter 21. And chapter 21 was based around the electrostatic force. So the electrostatic force, as a reminder, the magnitude of that force is K QQ over R squared. And since we're talking about a magnitude here, just to be safe, we'll go ahead and throw some absolute value bars around all of these things. We know that the direction of the electrostatic force comes from a diagram, and then we calculate the magnitude like this. It is also a vector, so we had to split it into its x and y components if we ever need to add the vectors together. We have more than one force. Now, I also made mention last week of a comparison between this equation and the gravitational force equation. The gravitational force had a magnitude of G big M little m over R squared. And when we covered gravitational force last semester, we started off by calculating the gravitational force between 2 objects. And then we said, okay, but what if we wanted to just talk generally about the effects that a mass has on the space around it? In that case, we need to develop something called the gravitational acceleration. And the way that we found the gravitational acceleration is we roughly just divided out the little mass that is experiencing the force. And then you get this expression, G big M over R squared. And this just tells you that if I have a planet of mass m, any object that's located at a distance r will have a certain acceleration. For everyone sitting in this room with the mass of the planet Earth and you a distance of 1 Earth radius from its center, each of you is experiencing 9.8 meters per second squared. All right, that's physics 1. We did that a ton. Now, what we did not do with this equation of physics 1 is we did not define this to be something called the gravitational field. That is new, but it's just a matter of assigning a word to it. And you've probably heard gravitational field maybe in a context of science fiction or something like that, a gravitational field around a planet. And that is in fact just talking about the acceleration due to gravity around a planet. Now, just as we defined the effect that a mass has by virtue of its gravity on the space around it, we can define the effects that a charge has on the space around it by virtue of its charge, of a charged object. Now, unlike in this definition, where we basically just took F, set it equal to ma and divided by m, now what we want to do instead is we want to copy the idea of dividing out the small thing that is experiencing the big force. So in this case, that would be this little charge Q. And when we divide out that little charge Q, we define what's called the electric field. Okay, big Q over R squared. A couple notes. This isn't quite a full definition yet. So I just want to mention that this is just, again, for a magnitude of a vector. And then we can put the absolute value of Q in there. And the way that we're going to do this is we're going to still, just as we did with the force, we're going to use a diagram to indicate our direction. And the rule is that a positive electric field will produce a vector that moves away, or I should say positive charge. I get that right. Positive charge produces an electric field that points away. A negative charge will produce an electric field that points toward the charge. And we'll do a little bit of this. You'll be fine with that. I think most people get those sign conventions all right. But just as we did with forces, we will draw a diagram to determine our direction, and then we will perform a calculation. That should be step 2, not step 3, huh? Perform a calculation using KQ over R squared, and if we need to, do some vector sums. All right. So let's go ahead and do one. We're going to start off. Last week, we did, I think, 3 charge arrangement problems. So guess what? We're going to start off with a charge arrangement problem. Then we're going to step the difficulty up quite a bit. But at least for the first one here, we just have 3 charges arranged in an isosceles triangle. 1, 2, 3 isosceles right triangle, which is very nice for us to deal with. They each have names 1, 2, and 3. And I'm not sure. I hear some chatter. Right. So okay. So we have, let's see, the side lengths here are A and A. You don't need to list that. This is the diagram you're going to get on your homework. But anyway, so yeah, so we have the same distances. Now, with the electrostatic force, last week, we had to pick one of these charges and determine the electric force on that charge and add them together. With the electric field, though, we can just look at a single point in space where no other charged object exists. And in this case, they're going to pick this point, which is just sort of equidistant to everything. And so it ends up being halfway between 1 and 2, and also that same distance from 3. We'll talk about what the distance is in just a second. Now, we have a procedure that you could do where you can go around to each of the charged objects and you can determine the direction of the electric field from the diagram, calculate the magnitude of the electric field, break it up into the X and Y components, add it together, and proceed from there. I know everyone can do that. What I want to start impressing in you, though, especially because we want to prepare ourselves as we attack these problems for quizzes and for exams where time constraints are an issue. So I want to start emphasizing the idea of looking for symmetry in the problem that helps you simplify it. So in this problem, for example, Q1 and Q2 for everybody are going to be identical. For me, it happens to be a charge of positive E. So these are maybe protons. And charge 3 has some other charge. We'll call it, that'll be different for everybody, but I'll do plus 2E. And as a reminder, E is the elementary charge, which is positive 1.6 times 10 to the negative 19th coulombs, if you needed that reminder. E is not electron, it's elementary. I'll probably mention that 4 or 5 more times before we're done with this part of the class. All right, so yeah, so as I mentioned, we want to look for symmetry here. So what you'll notice is, look at charges 1 and 2. 1 and 2 have the same magnitude of charge. Okay, so that's setting off like a light bulb right there. See, okay, I have the same charge on opposite sides of my point. Furthermore, we've defined this point to be exactly in between those two charges. So they've got the same charge at the same distance. Keep in mind what your electric field equation looks like is KQ over R squared. What are the variables here? Charge and distance. So if we got the same charge and distance, then the only thing that we need to really pay attention to here is the relative directions. So let's take a look. I'm going to use sort of color coding here. Go ahead and let particle 1 be the positive, be the red color here. It is a positive charge, so we know the electric field is going to point away from particle 1, which means at this blue point here, it's going to point down and to the right. We'll let charge 2 be blue. You could also label them if you'd like, but I'm just going to make a point here. Charge 2 also has a positive charge, so the electric field will also point away from charge 2, which at this point will be up and to the left. So if it wasn't immediately obvious by their location on opposite sides, now you see graphically that their electric fields point in opposite directions. We know that they have the same Q and the same R, so those are going to cancel out. Those will be the same, and the magnitudes are the same. And the overall message here is that I can cancel out these two electric fields without having to actually go into the nitty-gritty of doing the calculation. This is going to save us a lot of time. Now that we've done this, the only electric field that we need to calculate is the charge 3's electric field. Again, it's going to point up and to the right. This problem, though, very nice. They're just asking us for the magnitude. Since we've graphically canceled out 1 and 2's contribution to the electric field, we just need to find the electric field due to particle 3. And that is going to be K times Q3. And we'll go ahead and put absolute values just to be safe, over R squared. Now, for that R squared distance, what is the distance going to be? This might take a little bit of geometry to get. We need the distance from here to here. I know that this side is A, and there are multiple ways that you can get this distance. The way that I got it was just looking at this and saying, all right, this right here I know is a square of side length A. And if I have a square of side length A, the diagonal is A root 2. And then I just want half the diagonal. That's a root 2 over 2. Excuse me. And then that quantity will be squared, and it'll simplify from there. Cool. Symmetry, look for symmetry, look for simplification. One other note that I want to make, just real quick while we're looking at this equation. Last week I defined K as 8.99 times 10 to the 9. And it has units of newtons, meters squared per coulomb squared. Those units just exist to get you newtons out when you multiply everything else. I just want to make mention that as you're reading through textbook and you're watching other lectures and other videos and things like that, sometimes you're going to see K defined to be 1 over 4 pi epsilon naught, where epsilon naught is 8.85 times 10 to the negative 12, whatever. You're totally fine to use K. I'm going to use K for the simple reason of clutter as we're doing calculations, because these equations are going to get longer. But I just want to mention, if you start seeing epsilon naught or you're trying to match things up, just keep in mind that those are identical constants. It's just another way of writing a constant out. All right. So we have individual charge point particles, charge point particles. Not too bad. We did a bunch of those last week. There's another one there. We're going to do one more of those for problem number 5. And this is specifically an electric dipole. Here's what an electric dipole is. You have a positive particle and a negative particle. They have the same charge. They're separated a short distance. That's it. It's an electric dipole. I don't know why they make it a fancy thing. There's some like fancy equations for the dipole, whatever. There's always just one homework problem. And then, once every 4 semesters, it's an exam problem since the beginning of time. All right, so to copy down our diagram here, they are going to ask us about a point P that is some distance away, but explicitly, it is offset from the exact center of the dipole. So it has to be like on the axis. If it's not, then we can't really do this. I mean, we could do the problem, but it's going to get very hairy very quick. All right, so they define some distances for us. They define this distance from here to point P as little r. I don't love that because little r is the variable in our kq over r squared. I'm just mentioning that right now. And then they also define the distance here. I can do that again. Let me try that one more time. They define this distance as d over 2. And this distance also has to be d over 2. All right, you have the diagram there in your homework problem. Now, again, as we did before, we'd like to look for symmetry. And just as we did before, we're going to draw the diagram, see if any symmetry pops out of the diagram for us. So we'll go ahead and we'll start with the positive charge. We know that for the positive particle here, the electric field is going to point away, which means down at point P, you're going to have sort of down to the right. We can go ahead and call that E plus for electric field from the positive particle. And then for the negative particle, the electric field is going to point toward that particle. So if it's pointing from point P toward the negative particle, it's going to point down and to the left at just a very slight angle. Now again, because of the way that we've set up this problem, first of all, they have the same charge, same Q, and they're the same distance from that point P. So we've intentionally, the reason why they ask us about this point specifically is to set up that symmetry to allow us to do some simplification. Does anyone see a direction where there's going to be some cancellation here, either the X or the Y? Good, in the horizontal, yeah, exactly. So I have, this horizontal component and this horizontal component. I don't know exactly what they will be, but I know I'll have the same Q and the same R in my KQ over R squared. And I also know that this has to be the same angle theta. Good. So I can write this as, let's say, E positive, the X component is equal to negative E negative X component, something like that. You could do it, we could get real fancy with the notation there, but essentially all we're saying is that those two cancel out, right? There's no X component that survives. So what does survive is we have the Y components of each. And so our net electric field is just going to be the sum of the two y components, right? But we could even go a step further and say, well, those are going to have the same magnitude because by the same argument that we used to cancel x, those have to be the same. So the net electric field then, if it's going to be the y component of the positive and the y component of the negative, it's just 2 times either one of those y components. Without sort of losing anything, we'll just go ahead and say it's a positive one. So we're just multiplying that by 2. If you don't see this, you can calculate the 2 different y components, add them together, you get the same answer. This is the important part, though, for solving it quickly, especially on a quiz or exam. All right, now that we have this set up, all that's left to do is to express the distance, because we want to do kq over r squared. Our distance needs to stretch from this particle to the point P. This is why I don't love that they use little r. We'll go ahead and call this distance, I'll say it's r prime, but we need to express it in terms of that little r. Little r is given in the problem, so I apologize for that. This is a hypotenuse of a right triangle with side lengths d over 2 and little r. So it has a length square root of d on 2 squared plus r squared. And that'll be the distance for both. We know the charge is given in the problem as little q. And yeah, so just to write this out explicitly, we'll have 2k, the little q given in the problem, divided by the square root of d on 2 squared plus r squared. Oh, and then that quantity is all squared. So yeah, that's your r is the square root stuff, and then we need r squared on the bottom, so of course that'll go away. All right. Have any questions here? Cool. So that's 2. Oh, I do have a question here. So the square root cancel. Yeah, exactly. Yeah. So the square root and the square cancel. And remember, you need units of meters squared in the bottom. So it makes sense that this square root and the square would cancel, you know, with meters squared down there. All right. So yeah, so we have 2 examples here of problems where we have discrete point particles that are charged. We now are going to take it a step up. And the way we're going to do that is by, rather than having point particles that are charged, we want to distribute our charge throughout space. Here's our first problem. And this is problem number 6. And in this problem, here's the setup initially. We have a circle of charge, but it's going to be 2 hemispheres. Let me try that one more time. That's a little bit better. We have a positively charged and negatively charged hemisphere. So this is plus q, and this is minus q, not hemisphere, semicircle. There we go. It's exactly half of it has a positive charge on top, half of it has a negative charge on the bottom. And they're going to ask us to find the electric field exactly dead at the center of the circle. Why are they asking us about that specific point? Because if it was anywhere else, we couldn't do it. Well, we could do it, but it would get very, very, very messy very quickly. All right. So we are going to do an integral in this problem. I'm just going to go ahead and give you a warning now so you can sort of get ready to see that. And we're going to build it up. But before we do, I want to discuss a little bit about the symmetry and what we can cancel out and how we can simplify just from our diagram. So for starters, as we look at the blue piece of the circle up at the top, we know that as we go around the circle, each little bit of circle is going to have a little bit of electric field that points away. I also know that they're all the same distance. It's the constant big R, the radius of the circle. They're all the same distance from the center. So that means if I were to take 2 points that are like diametrically opposed like this and draw the directions of their electric fields, this one would have an electric field pointing like that, and this one would have a little bit of electric field pointing like that. And by definition, they have to be the same electric field because it's a little bit of charge and it's the same distribution all the way around, and they're located the same distance away. So going around, if we picked a point here, you have electric field there. If we picked a point here, you'd have some electric field. Up here, you have net electric field down. What is the net direction of the electric field from the top going to be? Think about the cancellation here. I have a little bit pointing down and to the left and a little bit pointing down and to the right. Just like over here, what did we say canceled here? The horizontal, right? But because we had the same magnitude of the electric field pointing down to the right and down to the left. It's the exact same argument here. This little bit and this little bit will have X components that cancel. And so you're just going to be left with a net Y component downward. Is everybody good with that? Okay. So that helps quite a bit because now we just need to find the Y component of the electric field. Good, okay, we got it. The second thing that we can do is by the exact same argument, because negative Q, the bottom part, the red part, because this arc will attract the electric field, by the same argument, you'd have a little bit here and a little bit there, and the X's are going to cancel, and your net electric field for the bottom arc is also going to point down. And so what you end up with is you have the net from the top will point down, and the net electric field from the bottom one will also point down. They're going to point in the same direction. They have the same charge. They have the same radius. Point here is that we can simplify this quite a bit by just saying this is identical to having one piece that has a charge 2q. All right, I waved my hands a little bit. If you really want to see it yourself, you could do the integral for the top and the integral for the bottom, and then do the vector sum. But just for the interest of getting through the problems that we have this week, I'm just going to go ahead and say, all right, this is an isomorphic sort of problem that we can do a little bit quicker. Okay, so as I mentioned, we do need to do an integral. We know that. We know that ultimately we just need a Y component of the electric field. But the way that I can find the Y component of the electric field, the way I'm going to have to do it is I'm going to have to take each little bit of charge, and I'm going to have to find the little bit of electric field that's created by each little bit of charge. So we need to take our electric field equation, which is E is equal to KQ over R squared, and I need to turn this into an expression with differentials. I want just a little bit of charge to create a little bit of an electric field. What does that look like? Just dE, the little bit of electric field that's created by K dQ over R squared. So when we were doing individual discrete particles, you took your KQ over R squareds and then added them all together using vector rules. Now we're going to take the little dQ and we're going to add it together doing an integral, but it's sort of the same approach. We're treating it like a bunch of different little particles. Okay, so far so good, right? Hopefully this transition makes sense for everybody. Next thing is, as I mentioned, we're just looking for the Y component, so that's nice. We can say then that we actually want dEy, which is just K dQ over R squared. And how do we find a Y component? Well, so long as theta is off of the horizontal, then Y will always be sine. So I don't know necessarily how I'm going to integrate this yet, but everything I've done so far is allowed. And I know that I do need to integrate this thing right here in some fashion. I have to integrate this to recover the electric field. So how do I proceed? Well, the name of the game here is to get that dQ into something that you can integrate over. So I don't know the domain of Q, I can't integrate over it, but I can make some substitutions. So the first thing is that they're always going to define this problem so that your charge is uniformly distributed. I'm not going to write all of that out. But because the charge is uniformly distributed, what that means is that the ratio of the total charge to the total length has to be equal to the ratio of the differential charge to the differential length. Here's what that will look like in an expression that you can use every time for any of these integration problems. Total charge over total length is equal to differential charge over differential length. So as you're proceeding through these problems, your starting point for doing these integrals is typically going to be something like this, and then you might look at symmetry and boil it down and get something like that out. But you can always start here and proceed from there, so long as you're accounting for the different distances and different lengths. All right, so I know that I want to somehow integrate over the entire length. My length here, though, is not just like a straight line distance, because instead what I have is I have a circle. So does anybody know the name for the length, a little bit of length along a circle? Hey, there we go. Okay, some people got it. Yeah, arc length. This is called an arc length. And the arc length is defined as S, and it's just equal to r theta. So this is covered it maybe a little bit in the last semester, but there's a review. All right, so the length is r theta. Great. Now, specifically, I know that I want to calculate the differential arc length. So that would come from differentiating here. Now, in this problem specifically, I know that my radius is constant, right? So I don't need to do like a product rule or anything on the right-hand side. I can just say that the differential arc length, ds, is equal to my constant r, which we'll call big R, times d theta. Sorry, I'm kind of scrunching up here. So using both of these now, I'm going to adapt this equation, and then I'm going to do a substitution, and then we're going to go ahead and integrate. So keeping in mind, for this problem, I happen to be given the radius big R and the charge Q and nothing else. So I know that I want to get this in terms of just R and Q. So that's going to be the reason I'm going to do a little bit of the substitution that I'm going to do here. Let's go ahead and proceed. So we know Q, big Q, that's fine. We can actually go ahead and substitute in 2 times little q if we want, because that's going to be our total charge. Over the length, what is the length of half of a circle? That would be 2 pi r over 2, or pi times r. You could also use the arc length equation if you'd like. We said this is equal to the other side where I have dq. I want dq ultimately for the substitution, so I'm going to leave that up there. And then dl on the bottom is just going to be r d theta. We're just substituting our arc length right there for the differential length. All right, this is looking pretty good. Go ahead and solve for dq. As I said, I ultimately want to do a substitution here. When I do that, my r's are going to cancel, and I'll have 2 times little q d theta over pi. Is that good? That looks good. All right, tight. So take a look here. Ultimately, our goal in integrating this is to get everything in terms of either a constant or the variable that we are integrating with respect to. So what are we ultimately integrating with respect to? D theta. Theta can be our only variable if we want to integrate. Is everything else going to be constant? Q is a constant, pi is a constant, k is a constant. Is r a constant here? Or does r vary as we move around the circle? No, it's going to be constant here. It won't always, but here that little r is going to be the radius of the circle, which we'll call big R. Good. And then we have sine theta, which we're going to go ahead and integrate. All right, so let's go ahead and do our substitutions. Each one, I sort of just ran through them, but let's write them out real quick. So we have d e sub y is equal to k times dq, we're replacing with all this junk here, 2q d theta over pi. That's just replace dq. On the bottom, we have r squared. And as I just mentioned, that's big R. So let's go ahead and put big R squared down there. Big R, as far as I use it, will always be a constant value. Little r will be a variable. Great. And then we have sine of theta. All right. So again, constant, 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 constant. Our only variable is theta, which is great. We're going to integrate with respect to theta anyway. Let's go ahead and do the integration. I'm going to flip slides and I'm going to clean it up just a little bit. I'm going to pull out all of my constants. So that's going to give me d e sub y is equal to, pulling out every constant, we have 2q a k over pi r squared. And then what's left over is just sine of theta d theta. Note, this is going to be unitless. These units work out. So it's a quick check if you want to make sure you're in the right shape. And as I said, now we want to integrate it. So if we integrate dE sub y, we're going to recover E sub y, great. And then the right-hand side, we want to integrate sine of theta d theta. And we need to define our limits of integration. The way that we've set this problem up is that we're just integrating over the first and second quadrants right here. So that's from theta equals 0 to theta equals pi. There are other paths we could have taken that would have given us something else, but as long as we input the proper limits of integration, then we're good. And then you just integrate that. What's the integral of sine? Negative cosine, and then negative cosine of pi is -1 minus negative cosine of 0 is +1. -1 minus 1 gives you -2, right? No, it's negative cosine, so there's another negative in the front. Anyway, you end up getting 2. I trust everyone can do the integral there, but you'll end up getting, your total will be 4 qk, or qk on pi r squared. All right, not a crazy integral, which is more than I can say for some other problems we're going to do. Got any questions here? Yeah.
You double that since there's also a negative field, not only counts for half hemisphere, is that for the whole?
This is for the whole top and bottom.
Oh, it is.
The reason it covers top and bottom is because of this simplification where we said that this arrangement with the positive 2q is equivalent to having this arrangement with the positive and negative. So yeah, you could have also just done over 1 and then multiplied by 2 at the end. Question?
I was gonna say, do you have time to quickly go over the steps again?
Yes. Yeah, let me do like 30-second real quick. All right, so where do we start? I start off with this and this. Those are the 2 tools in my toolbox. What I want to do is I don't want to integrate over Q. I know I'm going to integrate over something to do with space. So I want to integrate over an X, a Y, an R, a theta, something like that. So this equation is the one that will enable us to do that substitution. Before I do that, though, I'd like to look at some symmetry, see what stuff cancels out. If I don't look at symmetry, if I don't notice that I only have a Y component for the electric field, then I would need to integrate for both the X and the Y, and the integral in the X would go to 0 because you'd be integrating this exact same thing, but you'd be integrating a cosine theta and that would go to 0 when you integrate it. Okay. So yeah, so I'm saving myself just a little bit of time by saying, oh yeah, that's all in the Y direction, right? Because there's symmetry here, it'll all be in the Y direction. So I let this turn into this, and then I see that theta is going to be the thing that varies. So that's a little bit of a hint that says, all right, maybe I want to get dq in terms of d theta. How do I get dq in terms of d theta? Well, the charge is distributed along a circle, and the length of a circle is an arc length. So that means I need to define the arc length. And ultimately, I want to replace this dl with a dx or a dr or a d something or d theta, some spatial variable. And so it's the arc length formula that lets me do that. So I do the arc length formula. I replace the other stuff, q and l, just in terms of stuff given in the problem. And now that I have this, I know I want to substitute out dq. So I just solve this for dq. And once I have that solved for, I can plug that in. And now I can double check that everything here is either a constant or in terms of my integration variable. Q, pi, and r, constant, theta is my integration variable. I'm good to go. And then I just do the integral. Cool. Yeah.
How do you know that you need to integrate to solve this? Is it just because there's like a continuous charge in the arc length?
Yeah. So it's two things. First of all, the charge is continuous, like you said, and it's continuous. It's distributed throughout space. But also each little piece will contribute a different amount. So either, okay, chat is blowing up. So either you'd have either it'd all be the same magnitude, but in different directions, in which case you have to deal with that using integral, or yeah, they each contribute a little bit more or less. Like this little piece up here, this little dq up here is going to contribute all of its electric field in the negative y direction. But this little piece over here is going to contribute none or barely any in the y direction because it's all going to be to the side. So that's how we know, because the electric field varies as we move around the shape. and around the charge. That's how I know I have to do an integral. Okay, a lot of people talk about the quiz. Yeah, I'm not going over the trial quiz. It's worth 0 points. It's a review of math. We just reviewed some math, right? So if you need help getting into the quiz, I don't mind helping you next week. I will review again with the format of the quiz next week. But I think the most helpful thing for everybody right now is to do this homework as evidenced by that problem. Cool. All right. So this one, not a crazy integral. Next one's going to be a crazy integral, but now we know how to do them, right? So we're going to be able to do this even better. Okay. So here is our setup for this problem. We have a charged rod along the x-axis. It has positive uniform charge, and it has a length L. And then we explicitly place a point P right above the center of the rod. Why do we do that? Because if we didn't, this problem would get much more difficult. That point P is located a distance big R from the center of the rod. Now, again, to go back to your question, how do I know that I need to do an integral here? Because as I move from this end to this end, or from this end to the middle, as I move from one end to the middle, what I see is, first of all, that the direction of my electric field changes. So from this end, the electric field is going to point up and to the right, and from the middle, the electric field is going to point straight up. Also, the distance is going to change, right? So when I'm doing KQ over R squared, my R distance is changing. So that's two indications that I need to do some integral. So what are the tools I have in my toolbox? Well, as promised on the last problem, the two tools are dE equals K times dQ over R squared. And the other tool, when I have uniform distribution, is Q over L is equal to dQ over dL. We're going to use these two. We know we want to get rid of the dq. We want to substitute out something in terms of distance. So to go back to this problem, the way we set it up, I didn't mention that this rod is placed along the x-axis. We can set it then so that this rod extends from x equals negative L over 2 up to x equals L over 2. And then for any point along the rod, you just have some position x. So this will allow me to move along the length of the rod when I do my integral. And I could go ahead and actually set that up right here, right? That's just a straight up, we're just going to have Q over L is equal to dQ over dx. So that's actually dQ over dx. And in the problem, they give me Q and they give me L. So that's actually the easier part of this problem. dQ is equal to Q on L dx. And we can make that substitution or just think about it in our heads. That's going to work. Now, just as we did in the last problem, we can access some symmetry here because of the place that we have put our point P. Oh, I shouldn't have called that R up here. That should have been called point P. Because of the location of point P directly over the center of the rod, the X components here are again going to cancel out from each side. So the X component from this side and the X component from this side are going to be equal and opposite, and they will cancel out. If you don't see it again, you can do the two different integrals for the Y and the X. But in the interest of time, I'm just going to do the Y integral. So just as we did in the last problem, we just want the Y integral, which is going to be dE sub Y is equal to K dQ over R squared times the sine of theta. Now, what is the sine of theta? We've already started working on this little chunk. So let's go ahead and look at that electric field that's produced by that chunk. It's going to point up and to the right. And we know we want theta to be an angle off of some horizontal. So if we want that theta in terms of this picture down here, in terms of this diagram, this is going to be the same theta. We have parallel lines with the transverse cutting through it. If you don't see it, don't worry about it. You would be able to see it eventually. All right, so I know that I want to integrate with respect to x. Now my sine theta is going to be of some difficulty, and I need to substitute out sine theta. Unlike in the last problem where I integrate with respect to theta, now I'm going to integrate with respect to x. So I need to get rid of that theta. One other thing is I need to express my distance little r, which will be this distance right here. I need to express that in terms of x as well. So I'm going to start there because I see right here I have a triangle. This is a side length x, that's a variable. This is a side length big R. So the hypotenuse is little r. That means little r is the square root of x squared plus big R squared. And that's just the courtesy of setting the rod on the x-axis allows us to express the r that way. All right, so we have the variable that we're integrating with respect to, and we have a constant, so that's good for r. For sine theta, I said we need to do something to get rid of sine theta. We know that theta is this angle within the triangle. SOHCAHTOA tells us that sine of theta is opposite over hypotenuse. My opposite is big R, my hypotenuse is little r. So this will be big R over little r. However, we know that little r varies, and we know that we want to integrate with respect to x. So we need to turn r into terms of x. Luckily, we've just given an expression for that, but that's why our sine theta ends up being so wonky looking. It's going to be big R over the square root of x squared plus big R squared. This is just right triangle geometry with some variables in it, but nothing that you cannot do, I promise. All right, so let's take a look at all of our different terms here. X is our integration variable. Everything else needs to be a constant. So dq, we're going to have dx, good, and then we have constants q and l. For r, big R is a constant, good, x is the variable, fine. For sine of theta, we have big R, which is a constant, x, which is a variable, totally cool. Now let's go ahead and substitute each of these in and see what kind of mess we have created for ourselves. Here's what it's going to look like. We have dE sub y is equal to little k still hanging out. dq is our first substitution. We're replacing it with big Q over big L times dx. On the bottom, we have r squared. And r squared is the square root of x squared plus big R squared, quantity all squared. And then the last substitution we have is for our sine theta right here. We want to substitute in big R on square root of x plus x squared plus R squared. So that's just a replacement right adjacent to it. So it'll be big R over square root of x squared plus big R squared. It's not great looking, right? But I do know that I can integrate this. And I know that, first of all, I can pull my constants out. So that it's going to clean up a little bit. The stuff that varies is actually just the two denominators. And because of the exponents here, the first one is an exponent of 1, and the second one is an exponent of 1/2. So when I combine these two together, I'm going to have an x squared plus r squared to the 3/2. You would be able to see it later. Don't waste your brain power trying to figure out exactly how that worked. But on the next page, I'm going to go ahead and write down what the actual integral looks like. So we'll have a dE sub y is equal to pulling the constants out front. My constants are k, big Q, big R over L. And then what we'll be left with is 1 over x squared plus r squared to the 3/2 dx. Now I have an integral that I want to do. I can go ahead and say that I'm integrating into the left-hand side, it's just whatever, it's just a formality. But on the right-hand side, I do need to establish what my limits of integration are. Remember, I'm integrating over x, so I need to look at how I've defined x in my picture. In my picture, I'm integrating over the rod in x from x equals negative L over 2 to x equals L over 2. Now, the integral at hand, how do you actually do this integral? If you really want to, you can do, I think the trig sub is the most straightforward way to actually do this if you really want to do the integral. What I will mention is that in this class, they literally say, like I'm looking, like the solution manual literally says, look up in Appendix E. If you'd like to look up at Appendix E, item number 19 is a list of integrals, and you can just pull down the actual integral. What I'll tell you is that there's only like 3, and I think we're going to do them all in the homework. There's actually maybe one more that I'll cover before the exam, but there's really only like 3 of these. So if you just remember what the actual answer to the integral is, I don't tell people to memorize a lot of stuff, but these just happen to be the types of things where it's like, if you just remember how this integral works out, then you would save yourself any headache on an exam. Anyway, what's the actual value of the integral going to be? Well, once you integrate this, do trig sub, you'll get, for just this part, you'll get x on r squared times the square root of x squared plus r squared. And then you'll have to, integrate that from negative L over 2 to L over 2. And there are different solutions too. We could have looked for even more symmetry and integrated over half the rod or whatever, but yeah, and then you have the constants out front, of course. But yeah, anyway, that's something that you can evaluate, and then you can plug in the actual numbers that are given to you, and this will give you your net y component. As for the net x component, we already discussed that will cancel out. Fun, right? Physics too. At least though, they don't make us do the difficult integral. All right. We have 2 more minutes. I promise the last problem is going to be much quicker, much easier. We're done with the integration. I do just want to go over it though, so that you can do your homework and get on with your weekend, right? Enjoy your 3-day weekend. Don't do homework over the weekend, or do it, Tuesday. All right. So problem number 8, we have 2 parallel plates. We're going to come back to parallel plates in a few chapters. But all we need to know about the parallel plates right now is because of something going on with them, there's an electric field between them. And this problem has to do with what happens when you place a particle in an electric field. So in this problem, we have a proton and an electron. So this is your proton, and this is your electron. And I didn't mention this, but I will just mention that the electric field points in the direction that a positive charge will go. So that means that my proton is going to go to the right. On the other hand, a negative charge will just do the opposite of whatever positive charge does. So the electron is going to go to the left. One other thing that I need to mention is that we defined the field in terms of the force divided by little q. Rearranging that equation tells us that the force is equal to Q times big E. So if I were given a field like I am here, and I need to find out a force, I just take that field and multiply by the charge of each one of these. And then ultimately in this problem, we're going to set this equal to ma. This is just a motion problem. You're just getting an acceleration for these 2 objects. Then they ask you how long it takes for them to reach the same point, or where it's where they meet. Where do they cross paths? In other words, it's just like the ball problems from last semester. And so you just need to solve this for an acceleration. The acceleration is QE over m. And you find your acceleration, and then you just do motion, just 1D motion, physics 1, where you have, your initial velocities are 0, and you have your delta x is equal to x final minus x initial. The proton starts at x initial equals 0, and the electron starts at x initial equals the separation distance, and you just solve for when they're equal. I will mention that they do have different masses, so it's important to remember those, and I'll go ahead and give them to you just to save you some trouble. So first of all, the charge of each will be plus or minus 1.6 times 10 to the negative 19 coulombs. You don't actually, you could absolute values all this stuff anyway, because we know the direction of the motion from our diagram. Mass of the proton is 1.67 times 10 to the negative 27th kilograms. And the mass of the electron is 9.11 times 10 to the negative 31st kilograms. So the constants that you will need, you just plug them in with this equation, get your acceleration, and then do the motion. I'm confident once you let your brain rest, you'll be able to do a motion problem there as well. Okay, 1 minute over. I appreciate you all sticking around. Please feel free to comment up if you have any questions. Yeah, I'm going to post a recording of this one, Ainsley.